Anyone knows or has heard about what trigonometry is?
And we have basics, I guess, like cos and sine. You taught us that day. You remember?
Yes, very little. Yeah, I just barely introduced. Yeah, anything. But have you used trigonometry yet?
Not yet,
Anywhere
right?
in your studies?
It's mostly dealt with right angle triangles. Like that's what we know. You know, the base, hypotenuse, and the perpendicular.
Good. Yeah, that's pretty much what it is. We will see the connection between angles and distances. So let's go back to circle. So most probably, historically speaking, circle came up very early in time. So if we go historically speaking, there were triangles. So triangles, and triangle could be any shape, does not necessarily triangles, and there were circles. Let's think of these two geometries in particular, right? So that's a circle and that's a triangle. And the basic idea of a circle is that you start from a point and think of all points that is equidistant from that point. It's take a rope, tie one end of the rope on the ground and move around, and whatever you get is a circle, right? So the only specific parameter that describes a circle is a radius r. When it comes to angle, the point we want to keep in mind is that if you have three angles here, let's say theta, let's say alpha, beta, or alpha, beta, and gamma, right? That's Greek letters, alpha, beta, and gamma. Are you familiar with Greek letters?
We have heard it, but not that much.
Yeah, they're just symbols, usually like Latin. I mean, this is a good thing to know. Latin letters are A, B, C, D, and so on. And Greek letters are alpha, beta. I don't think C is exactly for gamma, but this is gamma, delta, and so on. Right. So that is a bunch of letters, and it has a name associated with it, exactly like A, B, C, D. They have sounds, and you can build words out of it. In Greek language, this is letters. In the Indian alphabet, we have ka, kha, ga, ga, na, right? So when all this was being considered, most of the literature was developed in or written down in Greek, and that's why this is that. Anyway, what we want to use is the fact that for any triangle, the three angles add up to what is that?
180 degrees.
180 degrees. That's what we want to use. So this is going to be the two basic things we want to use. So it is like everything else has to come out of this. Okay, so that's going to be our simple construction, that a circle will mean that the distance of any point from the center is fixed, and any three angles in a triangle add up to 180 degrees. So that's going to be our basic construct, if you want. Out of this, let's now think of a circle. So that's a circle, and now put a triangle inside the circle. And for that purpose, what I will do is that I'll have a straight line built like this. That's my center, and that's also if this is distance r, like any distance r, this also is r. Those are the same circle. In fact, this is also r. And let's say this is angle theta. And usually our goal will be that if this is angle theta, I can draw a straight line between these two. And if you notice, this triangle is isosceles triangle. Like isosceles triangle means,
Side
tell it again.
side angles.
Two sides of the triangle are exactly the same. So this is an isosceles triangle. That's R, right? If two sides of the triangle are the same, what can you say about the other two angles?
They are like
They will be exactly the same. Okay. So if this is an angle, let's say alpha, this will also be alpha. So if you know angle theta, what it means is that you can calculate angle alpha because the sum is equal to 180 degrees. So theta plus 2 times alpha is equal to 180 degrees. So we can calculate alpha, right? So alpha will be equal to 180 minus theta over 2. Right? That's one thing we can immediately conclude. But when I say trigonometry, our main idea would be, if I know this angle theta and I know the radius also, if we know that, can we find out what is this length A of this triangle? Can we say anything about this length? And historically speaking, when you had studied triangle, you had studied circle, that was the next higher challenge people took up. Can I calculate the angle A in any way? And this is called the chord, right? So this distance A, notice this is not the circular distance, this is a straight line distance, and that's called the chord of this particular triangle, and this is related to angle theta. So we will say that chord of angle theta is equal to A. Is that clear? Is the definition clear? Like if I have an angle theta, there's across from that angle theta, there is a distance, that's A, and chord of the angle theta will be A. So let's go to the other side of the board and let me do this again. So that's the circle again. And that's my triangle. And let me label this. So that's A, that's my B, that's this O, that's distance R, that's distance R, that's the angle theta. And what we have defined is that the chord of angle theta is equal to A, that's this distance A, right? That's AB basically. So A is equal to AB, the line AB. Like often in some of the notations, you draw a line above it to represent that that's the line AB. So that's a definition in a sense, and we would like to evaluate angle A somehow. Somehow can we find out angle A or have a procedure to get these distances given the radius and the angle theta. That is one thing we can immediately conclude. If that's angle theta, this is also radius R, right? It's a circle, so that's also radius R. That should be fine. And if that is the case, if this is an angle theta, this is also an angle, which I know what that is. That is 180 minus theta, right?
Yes.
And the chord associated with that is this, right? That's a straight line I can build. And that's also a chord. And I draw, let's say, let me say that's B. So what I have is a chord associated with 180 minus theta. It is 180 minus theta because I drew a straight line here. And that's equal to B. Correct? So that's just if the first side is A, that's B. And the question is there any connection between A and B? And the answer is yes, there is a connection. Tell that again.
Right triangle.
Yeah, why is it right triangle? So that's a very good observation. Good, very good observation that this is actually a right triangle. But then let me begin by asking, why is that a right triangle? So I think the point being made is, the suggestion you guys are making is, let me draw this again, emphasize that. That's the straight line, that's a center. And you guys are telling me that this is probably 90 degrees, right? That's 90 degrees. But tell me, why is that 90 degrees? So again, so this is the question is A, B, let's say C, and that's O, and that's angle theta. And this is, we are using, this is B, that's A, but whatever. Claim is that the angle CAB is equal to 90 degrees. Why?
By Pythagoras theorem, like chord of A square plus B square
is equal to diameter squared.
Yeah.
Yeah, that's correct. If it was 90 degrees, yeah, all that is true. What you're telling me is that this is R, that's R. Pythagoras theorem says that A square plus B square is equal to 2R the whole square. If this is 90 degrees.
Yeah.
Yes.
But I'm saying, why is it 90 degrees to begin with?
Something.
Only if I get that,
Because it-
rest everything follows, right?
No, because it proves that theorem that always A squared plus B squared. That's why it's 90.
No. Hey, okay, again, our rules are that, so there is some, so we have to go by the logic, right? The only thing I can use at this point is the sum of angles is 180 degrees
Yeah.
and the circle,
Yeah.
correct?
360.
The idea that all the points on the circle is a distance r.
Yeah.
And anything, so like isosceles triangle, we can use, and and you can use the Pythagoras theorem, but first we should know it's 90 degree, right triangle. Only then we can use the Pythagoras theorem, right? So somehow I have to conclude that this is 90 degrees. Yes, you're correct that that's 90 degrees. I grant that to you. But there's a very simple way of showing that that's 90 degrees. So here's the idea. So this is radius r and this is radius r. That means whatever this is the angle, let's say that's alpha. That's also alpha, right? So let me erase this and draw this a little bit more clearly. So if you allow me, so that's right. So if this is alpha, that's also alpha, agreed? Because it's an isosceles triangle.
Yes.
Yes.
And this is also an isosceles triangle. So if this is angle beta, that's angle beta. With me?
Yeah.
Yes.
If that's the case, now let's see this triangle. So there is beta. Like I want to sum up all the angles, which is equal to 180 degrees, right? That's beta. This angle is alpha plus beta, right? Which I'm claiming, or you are claiming that that's 90 degrees, hopefully. That's alpha plus beta, and this is alpha plus alpha.
Equal to
That-
180.
That's total is 180 degrees, correct?
Yes.
So there is 2 betas and 2 alphas. So 2 alphas plus 2 beta is equal to 180 degrees.
180 degrees.
The 2 goes away. So alpha plus beta is equal to 90 degrees. Yes, you guys were perfectly right. That's indeed 90 degrees, but now we know that, right? So first time back in, probably this happened maybe about 400 from our understanding, surely before 300 BC or so. They knew this, probably even before that. It's very hard to go and see exactly when they realized that. Pythagoras theorem is about 700 BC or so, at least if you go by the literature, it goes back all the way to 700 BC. So probably around that time, they realized that in a circle, if you draw a diameter and then two chords like this, then they form a 90 degrees. And after that, you guys are perfectly right. Once this is 90 degrees, that is a square plus b squared is equal to 2 times r square, right? Once you know this is 90 degrees, immediately you conclude that a square plus b square is equal to 2r the whole square, right? It's 2 times r, basically it's the diameter square. Is that clear? So notice the logic that I'm using. I have a circle, I inscribe a triangle in it, and I inscribe the triangle in such a way that one of the side is a diameter. And if that one side is a diameter, then the angle that it subtends has to be 90 degrees using this very simple idea. And once that is 90 degrees, we have Pythagoras theorem telling that a square plus b square is equal to 2 times r square. There's one more thing we can conclude here a little bit, and that is that what about angle beta? Like, what is the connection between beta and theta? Is there any connection to begin with? So again, let me go. So the question is, let me draw that here. So the question is, draw it again, draw the same diagram again. So that's R. Have a straight line, and this time I draw the dotted line here. This is angle theta, and we called this beta. But what is beta in terms of theta? What's the connection?
There is a theorem that states that the exterior angle in a triangle is equal to the sum of the interior opposite angles.
Very good. Very good.
Yeah.
Very good. So it tells that the sum of the interior angles has to be equal to this. So that's very good. So, and this is, we know that this is an isosceles triangle. So this is, if this is beta, that's also beta, right? So what we can say is beta plus beta, and the theorem that you're talking about is basically saying that beta plus this angle, the interior angle here, has to be equal to 180 degrees, but that is 180 minus theta, right? Plus 180 minus theta, correct? That's that angle here has to be equal to 180 degrees, correct?
Yes.
So 180 goes away. So 2 beta minus theta is equal to 0. That means beta, so 2 beta is equal to theta, so it's beta is equal to theta over 2. That's nice. So we are saying beta and theta are connected. It's, in fact, it is exactly half of that. If this is 60 degrees, that's 30 degrees. If this is 30 degrees, that's 15 degrees. If that's 10 degrees, that's 5 degrees, right? So beta is equal to theta over 2, right? Good. Okay. So again, the steps, if you notice, we said there is a triangle and a circle. In the angles of a triangle add up to 180 degrees. Circle points on a circle are equidistant from the center. we said that if we inscribe a triangle with one of them being the diameter, this is 90 degrees. And in fact, this is 90 degrees and this angle theta and this beta is connected. This is theta over 2. Right. So now so this is where we begin our definitions, right? So our goal was, notice that if I have an angle, I would like this distance, which is a chord. Chord of angle theta was A. Chord of angle 180 minus theta was B. I would like to find those A and B. So again, this same idea. So this is a, now I can forget the circle and just draw about the 90 degrees. That's my A, that's my B, and that's 2 times R. Right? And that is this idea that this is theta, but this is theta over 2. Right? That's that angle theta over 2 there. And this is chord of angle theta. And now I'll make some definitions. Notice A square plus B square is equal to 2 times R the whole square. So we will define, so these are definitions. And the first we will define and then find some angles and then come back and use them. We'll make a table basically. And that is what historically was done. And that's what trigonometry is about. Once you find theta, then you can use it again and again. So the definitions will be sine of theta over 2. Right? So this is the angle theta over 2. That's how we are defining. But later on, we will redefine this to be angle theta itself. But for now, the way I have developed it, this is for angle theta over 2. That's equal to, get this angle opposite to that angle. So that's A. That's angle A divided by, so opposite to that angle is A, divided by the hypotenuse, that's 2R. So notice opposite to angle. So opposite means opposite to angle. And divided by hypotenuse. That's a definition in a sense. And that is basically so that if I know the radius of the circle and the angle theta, that will allow me to calculate A in this manner. If I know this sine somehow, but we'll see how we can try to find this sine using some simple ideas. One more definition, cosine of theta over 2 is equal to, so that's cosine will be, now notice this side is adjacent, so this, the reference is the angle, right? Given this angle, the side B is adjacent to that. There are 2 sides adjacent to that. Hypotenuse is special, so we don't want to deal with this hypotenuse. Other than the hypotenuse, there are 2 sides. One of them is opposite to the angle. The other one is adjacent to the angle. So we're talking about the side that is adjacent to the angle. So that's adjacent to angle over hypotenuse. But that seems to be just random definitions. The idea would be again that to get A and B if I know angle theta and B, but for that I need to know the sine function somehow, or whatever the sign means. This is symbolic. At this point, I haven't done much, right? What is this sign? I really don't know, but we will find ways to calculate this. There will be this, we'll find this iteratively. If I can get it for one angle, I can get it for the next angle, and so on. So we'll find a way for that. But before that, it seems like there is this angle theta over 2, y theta over 2. And this is how in the original times it was defined, but in modern trigonometry, this is actually angle theta that is more important. And let's see why that is the case. So let's very quickly switch over to angle theta, and this is how you can do that. Any questions until now?
No.
Right, is that very clear?
Yep.
Okay. Okay, so again, we have this circle. That's the center, so that's your right triangle, that's right triangle, and that's the center.
So you forgot to change the camera.
Oh, I forgot to change the camera, thank you. Yeah, that helps, otherwise you cannot fall. Okay, good. Okay, so again, I drew the same triangle. This is the center. One of them is the diameter, so this is side A. That's the chord A, if you want, that's a chord A, and this is angle theta. And if this is angle theta, we know that this is theta over 2. But now stretch this out. And then I can draw this and draw this. This is 90 degrees. This is also 90 degrees because that's symmetric, right? It's perfectly symmetric. That's 90 degrees. If these two 90 degrees, this is also 90 degrees because this is also a diameter. That's also 90 degrees. That's also a 90. So it's a rectangle I have got. So, and in this rectangle, we are working with this angle theta over 2. Let's divide this rectangle into exactly 4 pieces. And let's think about this triangle here. 1/4 of the triangle that is formed, that will have exactly the angle theta over 2 in there. And then we have angle A over 2, but the radius is exactly the same in there. So instead of working with this triangle, we can work with this tiny bit of the triangle, and what we have is, so now if I were to draw that triangle in there, oops, so that's A over 2 now. This is B over 2, and this is angle, this is just the distance R. So instead of working with our original triangle, we can as well work with this triangle. And in that place, we define angle sine theta over 2 is equal to A over 2R. Right, but this time notice opposite over adjacent. Maybe I should emphasize that even though it comes out to be exactly the same, the structure is slightly different. So it is A over 2 divided by R, which is of course A over 2R. And that's how we see it these days, right? And this is how we define this. Theta over 2 is equal to B over 2 over R, which is exactly the same as before. B over 2R, right? But this is the triangle we are always talking about. So in modern ways of defining our sine and cosines, what we do is center, draw the straight line, and this is probably how I explained to you on the first time when we met. So you would say that this is the right triangle, which seems to have nothing to do with your original triangle, but they're exactly the same. That is one, if you want 1/8 of that triangle. So that's your opposite will be A here, like this is A over 2. So this is, let's say, this is A now. This is your R, and let me keep it A over 2, and this is B over 2. Okay. And that's how you, and this is angle theta over 2. Of course, I could have started with angle 2 theta and everything goes through. Now, notice we have said that a square plus b square is equal to 2 times r the whole square. Right? If all this is true, whatever we have done, then that's true. Divide out by that, you have a over 2r the whole square plus b over 2r the whole square is equal to 1, correct?
Yes.
If this is true, that must be true.
Yes.
And this is your first identity you learn in your trigonometry. If a over 2r, that's a over 2r, that's sine theta, right? That's sine of theta over 2. That's sine square, that's sine theta the whole square. Often you write the 2 on top of sine, plus cosine square theta over 2, that's equal to 1. That's your first identity. This is basically Pythagoras theorem, right? Sine square theta plus cosine square theta is equal to 1. If we were to redefine our theta over 2 as 2, that's nothing but Pythagoras theorem, right? Absolutely, exactly, identically the same. Okay, so again, goal is, if I know my distance r, circular radius, and an angle theta, I want to get a, right? Here we have still not really done that, but let's say we can know one angle. Can I get the next angle? That is how we will do this.
Shajesh, how did you put it as 1 at that one question? How did you put it as 1?
How did I put this? I just divided it to be by 2r. So I put this in, so I divided it out by 2r square in each term.
Everywhere you put divided by 2.
Yeah.
Okay.
Is that clear? So this is true because Pythagoras theorem is true. Then I divided it out by 4r square if you want. So that's 2r square, b over 2r. But then a over 2r is sine theta over 2.
Yes.
Right. So based on my simple definition of sine theta and cosine theta, now at least I have one identity, that whatever sine square theta is, which we don't know yet, the idea is that we can do something about it. We'll build a table for that. But that square plus this square has to be equal to 1. That's what we have learned as of now.
Yes.
Clear? Right. Everything coming from circles and triangles, right? As of now, but nothing new has happened yet, because I don't know yet what sine theta is. I have only defined it to be a ratio where neither do I know how to measure the chord, neither do I know how to do sine theta. But that's what we will try to do now. With me?
Yes.
Any questions? Karthik? Sriraj? Juan? Okay, so let me proceed. Now, can we at least calculate the sine and cosine of at least one angle, right? Let's begin with at least something. As of now, we have just been defining. So let's see. Before I forget, we are now I'll stop drawing the circle. The idea is that whenever you have a right triangle, you can always think of a circle that is inscribing it, right? So now we have a triangle. Like, remember, if you have a triangle like this, right? This is A, that's B, and that's 2 times R if you want, and this is theta over 2. In the way we are thinking of a circular, a triangle inscribed in a circle. I can make this angle whatever I want to, and let's take a very special scenario where this is 45 degrees. So that's 45 degrees. And let me also say that this is unit 1. Like that could be basically R, right? This is or this is A is equal to B. That's what I mean. So if A is equal to B, and let me also set that to 1. Right? I don't have to, but I can set that to 1 if I want to. Right? So that's 1. This is 1. And what is this distance? Hypotenuse?
√2.
Root 2, right? 1 square plus 1 square, and then like a square root, so that's √2. And remember our definition of sine of 45 degrees. Now I can define, right? I can actually calculate sine of 45 is opposite over hypotenuse. That's 1 over √2. So I mean, based on the definition, now I know that this is true. Agreed? I cannot do this for any angle because I won't know these distances at all the time. But for this triangle, I know that this is 1 over √2. And what about cosine 45 degrees? That's adjacent over √2. That's 1 over √2. Okay, again, exactly the same. And remember, we also have an identity, right? So sine squared 45, is that really true? So let's check this. Sine squared 45 degrees plus cosine squared 45 degrees. That's equal to 1 over √2 square plus 1 over √2 square. And that is 1 over √2 square is 1 over 2 plus 1 over 2. Indeed, that's equal to 1. So that's correct. So the identity works, right? That's so we are the first angle we have measured, or we have actually figured out for sine and cosine is sine of 45. That doesn't mean that we can do any other angle. So for example, if I were to tell you sine of 30, I don't know, right? So let's, for example, let's draw a triangle with 30, 60, right? This is that's the next goal we have. So this is 30 degrees. This is 90, right? And that is 60 degrees, let's say. Correct? And I can begin with at least one of them. Let's say this is 1, let's say this is 1, right? Can I say anything about any other side?
Yes. Yes.
And what can you say?
The ratio 1√3 2 2.
No, you're using knowledge, remember. You cannot use your existing knowledge. Everything has to be derived from what we have done before, right? You are assuming that sine of 30, so you're assuming that sine of 30 or sine of 60, I think that's what you're saying, is √3 over 2. But I would like you to derive this. For now, we don't know. We are going by history, right? We are really developing each step from the earlier step. Do you see my point, logic?
Yes. Yes.
So I can use sine 45 though, if you want to. Now that we have got sine 45. So how do we get this? So we again go to the circle if you want, or 60 degrees reminds us of an equilateral triangle, right? So basically make this an equilateral triangle, right? So let's say this is 1. If this is also 30 degrees, that's 60 degrees, and that makes it an equilateral triangle. So let's say this is length L, right? So what if this is how can I do this? If this is X, right? Let's say this is length is X.
Then
this is X over 2, correct?
Yes. Yeah.
Right? And this is, we said 1. But these 3 are connected using Pythagoras theorem. So X over 2 the whole square
Plus 1 square.
plus 1 square has to be equal to X square. Correct? That's 1 over 4. That's 1. Put it on the other side. So that's 1 is equal to 1 minus 1 by 4. So that's 3 by 4 X squared. Right? So X is equal to 2 over root 3.
Yes.
Okay, so now I know x here. So x is equal to 2 over root 3. So x by 2 would be equal to 1 over root 3. Right? So now I can try to define my sine 30 and sine 60. So let's begin with sine 30. Sine of 30 degrees is equal to opposite over hypotenuse. That's x over 2. Actually, I didn't have to go over all this. This is x over 2 divided by x. That's 1 over 2. Right?
Yes.
And cosine of 30 degrees is equal to cosine of 30 is adjacent over hypotenuse. So that's adjacent is 1 over x, which is 2 over root 3, which is indeed root 3 over 2. That's what you guys told me, right? Of course, that works out because that's how it was done probably to begin with. Again, we should check, does the identity hold? We have this identity that cosine square 30 plus sine square 30 is equal to 1. So that's 1 by 2 square plus root 3 over 2 square. That's equal to 1 by 4 plus 3 by 4. That's indeed equal to 1. That works, right? So identity again works, correct? So I have sine of 30, sine of 45. We can also get sine of 60, correct? Sine of 60 here is opposite over adjacent. So let me make some room here. So this was an identity check, right? So I have sine of 30 is equal to 1 over 2. Sine of 60, we will find out. Cosine of 30 is equal to root 3 over 2. And cosine of 60, we will try to find out, and then I can erase this stuff also. And sine of 60, just using our ideas, is opposite, that's 1, divided by hypotenuse, that's 2 over root 3. So that's root 3 over 2. There is a symmetry here that cosine of 30 is the same as sine of 60. And cosine of 60 is adjacent, which is x over 2. So that's 1 over root 3 divided by 2 over root 3. Root 3's cancel out, that's 1 over 2, right? So we have sine of 45, sine of 30, sine of 60. So 3 angles we have managed to calculate at this point based on our definition. Okay. Which means that if I have a chord, so what we have succeeded in doing is very limited. Our development has been very slow. If I give you a 45 degrees here and tell you that this is radius r, it allows me to calculate this chord here. Okay, our goal is to calculate this chords, right? So I can actually calculate that length here. For 45 degrees, I can do it for 30 degrees, I can do it for 60 degrees. That's it, nothing else. Okay, very slow progress. 3 angles we have calculated. Now tell me, what other angle can you come up with? Tell that again.
75.
75. And why do you say that? Yeah, maybe. But tell me how you would do that.
Yeah.
There is 90 and 0, right? Like 90 degrees.
Oh, yes, that's a good point. Yeah, we have couple of more angles. Very sure. Very good. Yeah, that's a very good observation. That if I say this is 0 degrees, right? That's a very, like if I really make this tiny triangle, then this is 1 and that's also 1. So yeah, I should add that sine of 0 is equal to, that's 0 over 1, so that's 0. And cosine of 0 is 1 over 1, that's equal to 1. And the same thing, sine of 90 degrees is equal to 1. And cosine of 90 degrees is equal to 0. Very good, very good. That's a good point. We should have actually started with these two, right? These are the most simplest ones. I started with 45 degrees. So we have 0, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Very good. And then I can get the chords associated with those angles. But that's very limited, right? With this definition, so it's very limited. We have to go and proceed and do more. And that's what I'm going to stop here today. And what I want you guys to think about, so hopefully next week we will again meet, and I will tell you how to do this for more angles. But meanwhile, I want you guys to think about, and can you think of any geometry that you know of? Like we use the geometry of an equilateral triangle, correct? And the idea is, can you get any other angle here? You said 75 degrees, or think of polygons maybe, or in general, historically, how it was done was that they found a way to cut half the angle. If I know 60, I can get 30 degrees. So if I know 30, I can get 15 degrees. If I get 15, I can get 7.5. And that was an idea, but that's way more, slightly more sophisticated. But the homework, I don't want to make it a homework because this is not a course as such, right? So we shouldn't have homework, but just ponder or just think about what else can you do, like from this limited scenario and this limited geometry that we have of a right triangle, right? Which is basically the idea that circle, every time you think of a right triangle, you want to think of it like that. Right? So it is inscribed as a inside a circle. So can you think of any other angle, right? Other than 0, 30, 60, 45, and 90, for which you can actually calculate this number. Okay, is the problem clear? Is the question clear? Just to think about, and I'll come back and give you a sophisticated answer to this, which will allow us to calculate for any angle. We will be able to divide it. So it's like a thermometer, right? If I know 0 and 100 degrees, then I can do it for 50 degrees divided by 2. Then I can do it by 25. Then I can do it for, so I'll keep dividing by 2, then I can do it precisely. And once I make that table, then I know the whole sine theta in a way. And this was literally done, historically speaking, in somewhere around 150 BC. They did it for until 7.5 degrees, and by Ptolemy, because they were interested in this in astronomy a lot, they really wanted to talk about at what angle the stars are, how much distance these stars make. So by 200 AD, they had it for 0.5 degrees. And that stayed like that because between 200 AD and 1600 AD, there was very little development in science. Just sort of stuck for various historical reasons. The development in science was very slow during that period. And then again, 1600, of course, they made the whole sine table for very reasonably, very precise numbers. But we will do that next time. So is it okay if we go slow? Yeah. And meanwhile, you guys think, tell me how, and feel free to refer. Okay. There's nothing wrong in referring, get ideas from existing literature, and tell me how you can get any other angle in a nice, clean way, simple, only using the knowledge that we have as of now.
Only using triangle and circle, right?
Correct. Or triangle and circles, or any other known geometry.
Geometry.
Yeah, like square, or maybe polygons are basically triangles.
Yeah, multiple. Multiple.
Yeah. Like regular polygons, you can actually draw using triangles. You can build polygons. Like,
yeah, if you got multiple polygons, it can become a circle, right?
Exactly. So those kind of things you're allowed to use, but try not to use any more knowledge that's there. Don't use modern knowledge. That's what I mean. You have to develop it from the scratch.
Correct.
Reasonable?
Yes.
Yeah. Okay, nice. So was this reasonable, useful?
Yes.
Okay. Nice. Yeah. Thanks.
Okay.
Thank you.
Okay, good.
Good night to you, right?
Yeah, for me, good night, and for you guys, good afternoon, good morning.
Yeah. Great.
Yeah.
Thank you.
Thank you.
Bye-bye.
Bye-bye.
Cool. Bye. Okay, Joanne. Bye. Karthik.
Bye, sir.
Bye.